Are there any questions from the audience or from people, from students from home? Yeah, so sorry for this technical part. I assumed that you told the definition of the determinant with these sums or all permutations of n numbers, so of the first n numbers. If you didn't, then it's just too technical to go over this. So this is the usual definition of the determinant of the matrix, and from this you can prove that the Vronsky really satisfies this differential equation, and assuming that it really satisfies this differential equation, it's possible to prove that either it's always zero or it's never zero. Okay. Let's go to characteristic polynomial of the differential equation. We've already we already defined the characteristic polynomial of the differential equation. So let's recall this. We have differential equation of order n. Let's say it's homogeneous. By this algebraic trick of transforming the differential equation to first order system of differential equations, we did this last time, that the system becomes vector x prime of t is equal to, and then here we have this matrix of the system, and this matrix of the system is a specific one. So it has in the first n rows, it has ones on the upper diagonal and 0 elsewhere. So do you see why is this true? How this follows that for each differential equation, no matter which one, the corresponding matrix of the system is the same in the first n minus 1 rows. Why does this follow? From where does this follow? What is, for example, this first row saying? So first row multiplied by our vector says that, so we just multiply the second entry of the first row with the second entry of our vector x, so we get x2 of t. And this x2 of t is the same to the first entry of the first row, which is of the left hand side, which is x1 prime of t. And then the second row multiplied by this vector x tells us that only the third entry of the second row is multiplied by the third entry of vector x, so it's x3 of t. And on the left hand side, we get x2 prime of t. So those first n rows are just correspond to this algebraic trick of introducing new variables. While in the last row, we have to include our differential equation, which is xn prime of t is equal to, so now we express, as we did the beginning of the first hour, we express xn prime of t out of this differential equation. So it is minus an minus 1 xn minus an minus 2 xn minus 1 and so on, minus a0 x1. So we plug those coefficients in the last row. So an minus 1 is here, then an minus 2, an minus 3, and so on, a0 minus a0 this is what we told already last time. The solutions of this system are of the form e to lambda t times v, where lambda is an eigenvalue of A. So lambda is an eigenvalue of A, and V is the corresponding eigenvector. But if you go and try to compute the eigenvalues of A, so the eigenvalues of A are the zeros of the determinant of A minus lambda identity. The eigenvalues of A are roots of the polynomial determinant of A minus lambda identity. And let's see what's this determinant of A minus lambda identity. Because probably you didn't do this trick at linear algebra course. So let's do it. Determinant of A minus lambda identity. It is determinant of this matrix. So we have minus lambdas on the diagonal. And in the last entry of the diagonal, we have minus A n minus 1 minus lambda. And then we have ones on the upper diagonal. And in the last row, we have minus A0, minus A1, and so on, minus A n minus 2. Okay, and how would you compute this determinant? What would be the easiest way to compute this determinant? You've said before previous hour that you know how to compute determinant with respect to a row or a column. So which row would you choose? Yes. So it's the most convenient to take the last row, because then what remains is always diagonal. So let's compute this determinant with respect to the last row. So what we have to do, so we take this it's the product of the entry, so minus A0 times, then we have to forget about the first column and the last row, and what remains, the remaining minus 1 times n minus 1 matrix, the determinant of this matrix occurs here. So what do we get here? What's the determinant of this matrix which remains? What kind of a matrix is it? Not only it's not only diagonal, it has something also below diagonal. So it has ones on the diagonal and minus lambdas on the lower diagonal, the first lower diagonal. But when we have a lower or upper triangular matrix, what's the determinant of lower or upper triangular matrix? Yes, so it's just the product of diagonals. So this is lower triagonal matrix, so it's just the product of diagonals, so it's just the product of ones here. And I forgot something here, so I also have to multiply by -1 to some power which is dependent on the position of this -a0. And so what is here? -1 to the sum of the sum of positions of a0. So this a0 is in nth row and first column, so I have to sum here n plus 1. And then let's move to another entry, to -a1. So here we have to forget about the second column and the last row. What we get here is plus -a1 times what is the determinant of the matrix without the second row and the second column and the last row? Sorry, minus lambda. Yeah. It's again lower diagonal, and here we have minus lambda and then ones on the diagonal, so minus lambda times -1 to n plus 2, because -1 is in nth row and second column. And we proceed in this way. Let's do another term. So in another term, we have to forget about the third column and the last row. Minus, so plus -a2. I will write this -1 to n plus 3, not to forget about this -1 or +1. And what do we get here? What's the determinant of the matrix without third column and last row? Yes, minus lambda squared. So here we have again the lower diagonal matrix. In the first two diagonal entries, we have minus lambda, and then we have ones. So it's minus lambda squared, and so on. The same trick works up to the one entry before the last, but the last one is a little bit different. So the entry in the column n minus 1 is minus a n minus 2 times, here we have n minus 2 lambdas times -1 to the position, which is 2n minus 1. And then in the last column, we get minus a n minus 1 minus lambda times minus lambda to n minus 1 times, and then we have -1 to sum of positions, which is 2n. If we if we factor out -1 to n, what remains from this first from the first summand? So we have here -1 to n plus 2. So -1 to n plus 2 is just -1 to n. So we can forget about -1 squared because it's 1. So a0 remains. So this is from the first factor. Then we look at the second factor. What remains is, so here we have -1 to n plus 3. We can forget about 2. So we get -1 to n plus 1. And -1 also multiplies by -1 because of this lambda. So in fact, -1 is raised to the power of n plus 4. So it's -1 because of this a1, then -1 because of lambda, and -1 to n plus 2 because of this part. So it's -1 to n plus 4. So altogether it's -1 to n. So here we get a1 lambda. From the third term, we get a2 lambda squared. Again, minuses, we have -1 to 1, plus -1 to 2, plus -1 to n plus 3. So it's -1 to n plus 6. So it's in fact -1 to n. That's why the sign is really plus here in the bracket. And so on up to this. This is because of this term. Then this is because of this term. And everything works the same up to this term, which is a n minus 2 lambda to n minus 2. But here in the last term is different from the previous ones. So last term is different. If we take a n minus 1 and multiply by the remaining two parts, we get a n minus 1 to lambda n minus 1. But then we also have this part with lambda. And this gives us plus lambda to n. And you see what we got here within the brackets. This is nothing else but our differential equation, where we, instead of the differential operators, we plugged in lambdas. So our differential equation was our differential. Okay, let me rewrite it. So our differential equation was x n derivative plus a n minus 1 x n minus first derivative plus so on, plus a1 x prime plus a0 equals to 0. And what we got here in the brackets is just replacing the ith derivative with lambda I. So we just replaced x, ith derivative of x with lambda to I. And this is what we call characteristic polynomial. So lambda to n plus a n minus 1 lambda to n minus 1 plus so on, plus a1 lambda plus a0. This is a characteristic polynomial of a differential equation. So if we go to the system, then we have to compute its eigenvalues. The eigenvalues of the system, of the corresponding system, are just the zeros of the characteristic polynomial. So this shows that we don't need to go to the system. We just use the system to prove this fact. So how to solve such an equation, such a differential equation of order n? We introduce its characteristic polynomial and compute its roots. So to obtain the solutions of the initial DE, we compute the roots of the characteristic polynomial. And I will write them here. So let's say that the roots. So how many solutions does a polynomial of degree n has? N? Is this clear, or is this some deep fact? It looked clear to me when I started studying mathematics, but in fact it's theorem of algebra, which is a deep result. So every polynomial of degree n has n roots. This looks trivial from the factorization of the polynomial, but it requires proof. So it has n roots, are roots of p lambda. And now, what are the solutions then to the differential equation? So we have a differential equation. We formed the characteristic polynomial. We computed its roots. And what are now the solutions to DE? So we need functions. So for now, we only have roots of the polynomial, which are real numbers, but the solutions of the differential equations are functions. So how do we form functions out of those roots? So if you recall, we were in systems. So if we worked with systems, we would compute the eigenvalues of the matrix A, which are precisely these lambdas. And how would we form the solution of the system then? Yes, so we would need corresponding eigenvectors. And so let's say that V1, here we will write only in brackets, so in parentheses, for systems, we would compute the corresponding eigenvectors. V1 up to Vn. And what are then the solutions to the system? The solutions are, so V1 times what? So V1, and what do we have to multiply it with? Because V1 is a constant vector. We need a function. So this vector must be a function of the parameter t. So what is the function here appearing? Do you recall? It's easy to guess if you have a diagonal A. So for a diagonal A, if the matrix A would be diagonal, here we would have x equals to x prime. So we could have x1 derivative is some constant c times x1. So what would be x1? What is the solution to this first order DE? By separation of variables, we have x1 dx1 or x1 equals to c1 times dt. So x1 is then in fact e to c1t, and here we have some constant k. So x1 will be of this form if we had diagonal system. But if we don't have a diagonal system, then this e to lambda t remains. Instead of the vector, which only non-zero coordinate on the first place, we take this vector v1. So the solutions to the system would be e to lambda 1 t v1, then e to lambda 2 t v2, and so on, e to lambda n t vn. This would be solutions to the system. But recall that, so when we went to the system, we in fact, the solution to our differential equation, if x1 was the solution to our, if x1 solves our nth order DE, then in the system, we need a vector of solution, vector which solves a system. Then x1 prime up to xn minus 1 prime, sorry, x1 n minus first derivatives solves the system. And this x1, but this x1 prime, x1 n minus first derivative is in fact e to lambda 1 t times v1. So this is one of those solutions above. So what is then x1? Yes, e to lambda 1 t times then the first entry of v1, which is some real number, but it is some constant. So here we have some v11. So and this v11 is just some constant, so it's parameter. So this means that we really only need to compute the roots of the characteristic polynomial, and then the solutions are those e to lambda 1 t parts, and we don't need to care about the eigenvectors. So if you go to if you do a translation to the system, then we also need to compute the eigenvectors, but here we don't need to, because we are interested only in the first component of this eigenvector. So if we return above, to obtain the solutions of the initial DE, we compute the roots of P lambda, and then the solutions are, I will write this with blue. So solutions are e to lambda 1 t, then e to lambda 2 t, and so on, e to lambda n t, and their linear combinations. Linear combinations. Okay. This is almost true. So so this is true. Yeah, the solutions are those and their linear combinations. If lambda 1 is real, then e to lambda 1 t is real, and we are satisfied. So if lambda 1 is real, then e to lambda 1 t is also real function, and we are done. Now, if lambda 1 is not real, then it's complex. Then lambda 1 is of the form alpha plus I beta, where alpha and beta are real numbers. Okay, but we don't want complex solutions, because e to lambda 1 t is then e to alpha plus I beta t, and we are not satisfied with the complex solutions because we will be solving real problems in which we need real functions. So we write this as e to lambda t. This part is okay because lambda e to alpha t. This part is okay because alpha is real, times e to I beta t. And we would like to somehow get rid of this I in the exponent. Now, what is this e to I beta t? How can we write this in the polar form? Do you remember Euler's formula? Yes, so it's cosine of bt plus I times sine of bt. This is Euler formula. So we have here e to lambda 1 t, and now we wrote it as e to alpha t times cosine beta t plus, and then we have I times e to alpha t times sine beta t. So we would like to claim that real part and the imaginary part of this function are also solutions to our dE. And my question is this true? And why is this true? So for now, we only have one solution, which is e to alpha t. Why can we claim that the real part and the complex part of this solution is also a solution? So we know that our polynomial in alpha in lambda 1 is equal to 0. What can we say about polynomial in lambda 1 conjugated? What's the value of this polynomial in lambda 1 conjugated? So what do you know about solutions of the polynomial equation if the coefficients are real? So they are either real or they appear in some they occur in some pairs. Conjugated pairs, yeah. So is this difficult to see? Yeah, it's 0. Yeah. So, but why is this true? So we have your polynomial, let's say lambda 1 to n plus some coefficient c1 lambda 1 n minus 1 plus coefficient lambda 1 n minus 2 and so on. How do I argue that lambda 1 conjugated also solves this equation? What can I do here from this equation? So if I conjugate both sides, what do I get on the left side? So conjugating the left side gives me lambda 1 to n conjugated is lambda 1 conjugated to n, because conjugation of the product is just product of conjugations, plus, and here what's the conjugated number of cn minus 1? Because it's real, because our assumption is that we have a real equation. So it's still cn minus 1 and then lambda 1 conjugated n minus 1 and so on, plus c0 conjugated, which is just c0, it's 0. So what we prove that really if p of lambda 1 is 0, then p of lambda 1 conjugated is also 0. But this works only if p is a real polynomial. So if p has complex coefficients, this is not true anymore, because when we conjugate, these c's should be also conjugated, and then we get another polynomial. So this is true for real polynomials. So this is true for polynomials with complex, with real coefficients. Okay, so e to lambda 1 t is a solution. what we just proved is that e to lambda conjugated t is also a solution. So e to lambda 1 prime t is also a solution of a dE. Okay, now we just repeat this derivation above. And in this derivation above, so lambda 1 conjugated is alpha minus I beta. So only plus goes into minus. So in this first equality, only plus goes to minus. In the second equality, e to alpha t remains, and then I beta t becomes minus I beta t. Then in this third equality, e to alpha t remains, and then cosine minus beta t plus I times sinus minus beta t. So e to lambda 1 conjugated t is, after this derivation, is e to alpha t times cosine minus beta t plus I times sinus minus beta t. Now, what kind of a function is cosine? What can we do with this minus? Can we forget about it? Because we can forget about it because it is an even function. Yeah. So it's symmetric with respect to the y-axis. So it's just cosine beta t plus. What about sinus? Sine of minus beta t. What can we do with this minus? Yeah, we can put it out because sine is odd function. We put it out. So in this second solution, the real part is the same to the previous one. The imaginary part is almost the same, only that it has also minus. And now, what can we do? How can we argue that the real part and the imaginary part of both really solve our dE? So we know that e to lambda 1 t solve our dE, and then e to lambda 1 conjugated t also solve our dE. What about their sum? Does the sum also solve our dE? Yeah, because we have a homogeneous one. So we started with a homogeneous one here. So we have, if we have two solutions, then every linear combination of solutions also solves the dE. And what is this sum? It's just 2 times the real part, which is 2 times e to alpha t cosine beta t. So that means if we also multiply everything by 1/2, we get this e to alpha t cosine beta t. And how do we get, by the same reason, how do we get the imaginary part? What do we have to do? Subtract, yeah, subtract. We subtract them and get 2i times e to alpha t sinus beta t. And to get rid of this 2i, we just multiply by 1 over 2i and get rid of 2i. Okay, so if lambda is complex eigenvalue which is not real, then we take the real part of this e2 lambda t and the imaginary part of e2 lambda t, and those are two solutions. So instead of e2 lambda 1t and e2 lambda 1 conjugated t, we can take its real and its imaginary part. Okay, these are two things. And there is another thing. What if some eigenvalue repeats? What if lambda 1 is equal to lambda 2 is equal to so on to lambda k? Then of course e2 lambda 1 t is equal to e2 lambda 2 t is equal to so on e2 lambda k t. So we don't get k different solutions, which we need. However, in this case, it turns out that the first one remains, e2 lambda 1 t remains. But instead of this e2 lambda 2 t, we have to put here t times e2 lambda 2 t. And then instead of the kth one, we put t to k minus 1 e2 lambda kt. And then we really have k different functions. It's not very long derivation of this, but let's keep derivation. Let's keep this derivation. Let's only look at the example so that you will see this is really true for in case we have a double eigenvalue. It's not very difficult derivation. It's one line derivation, but let's keep it. You will have it in notes. But let's say that we are solving the differential equation x double prime. It's just x minus lambda 1 minus, I will prepare the corresponding polynomial. So lambda minus 1 squared is lambda squared minus 2 lambda plus 1. So our differential equation, let our differential equation be x double prime minus 2x prime plus 1 is equal to 0. So this is our initial differential equation. The corresponding characteristic polynomial is the one written here. So it's lambda squared minus 2 lambda plus 1. And it was formed in the way so that 1 will be its double double root. It's just lambda minus 1 squared. So lambda 1 is equal to lambda 2 is equal to 1. So that means that this case 3 applies, and I claimed above that the solutions are e to lambda 1t. So we claim that the solutions to the differential equation star, that the solutions to star are e to lambda t, which is e to t, and t times e to t. Okay, how would you check that this is indeed true? How can we check in this specific example that those two are really solutions to the differential equation? Yes, we just insert, let's just insert those two into star and see that it is satisfied. So et double prime minus 2 et prime plus 1 so et double prime is just et. Of course, here it should be x. Sorry. So here, the initial differential equation is x double prime minus 2x prime plus x. If it was 1, then it wouldn't be homogeneous. So it should be x here. But the characteristic polynomial is the same, lambda squared minus 2 lambda plus 1. So here, you see, it's good to check the solutions, and then you see you screwed up something. So e2 second prime minus 2 e2 prime plus et. What we get, so the derivative of et is just et minus 2 et plus et, and we really get 0. So e to the power of t is really a solution of our dE. And then we do the same for the other candidate, t times et double prime minus 2 times t times et prime plus t times et. So let's first compute the derivative of t times e to the power of t. So what is the derivative of t times e to the power of t? Yes. So by the product rule, we have to take the derivative of the second one and multiply by the first one, and then we plus the derivative of the first one and multiply by the second one. And then what is the second derivative of t times e to the power of t? So it's the first derivative of what we've just derived. It's the first derivative of this function of the first derivative. And here we just take the derivative of every of the summands, and we get t times e to the power of t plus e to the power of t plus e to the power of t. So we get t times e to the power of t plus 2 times e to the power of t. And let's see if we've calculated everything. So let's see if it really cancels out. So we have from the first summand, we have t e to t plus 2 et. Then from the second, we have minus 2 t e to the power of t minus 2 times e to the power of t. And the last is just t times e to t. And what we see, so the first and the last summand subtract with the middle one, while the second and the fourth also subtract. So we get 0. And by a similar calculation, only in a more general way, we can prove this fact that we have if we have a eigenvalue or a root of multiplicity k, then the solutions are exactly those e to the root t, and then also t to the power, which is smaller than the multiplicity, times e to the power of the root times t. let's just sum up. So we are given a differential equation of order 2. These are the most important in applications. We will study vibrating systems, which are just differential equations of order 2 next time, the first hour next time. And we compute the characteristic polynomial, and this characteristic polynomial can either have different real roots. In this case, the solutions are e to lambda 1t and e to lambda 2t. It can either have conjugate roots, alpha plus beta, alpha plus I beta, and alpha minus I beta. In this case, the solutions are e to alpha t cosine beta t and e to alpha t sine beta t. Or it can have one double root. In this case, the solutions are e to lambda t and t times e to lambda t. And we will see next time that this t times e to lambda t is responsible for the occurrence, for the natural occurrence, which is called resonance. Because so you probably heard about resonance. Sometimes the bridges come into resonance when vibrating, and this means that in the limit when t goes to infinity, the amplitude of vibrating is infinite, and this is caused because of this part, t times e to lambda t. So if lambda is negative, then t times e to lambda t still goes to infinity when you compute the limit, when you send t to infinity. So this x2 part prevails. So this is really a very specific event when the differential equation with which you model your situation has double real root, and then the second solution goes to infinity, while all the other solutions just disappear. So e to lambda t when lambda is smaller than 0, which is the case when you study vibrations, lambdas are always smaller than 0. In this case, those e to lambda t when t goes to infinity go to 0. The same is true for the complex conjugate pair of solutions, because alpha is smaller than 0, and this e to alpha t part ensures that you really go to stabilize to 0. Okay, and for the end of today, let's only say something about how to solve the case when on the right hand side of this differential equation you don't have 0, when you have a non-homogeneous differential equation. So how to solve second order differential equation with a non-homogeneous, with a non-trivial and non-homogeneous part. dE of order 2 with non-trivial, non-homogeneous part. So we have x. We'll just go through 3 examples. We won't do the computations. You can do the computations. You will do such computations at lab sessions, and they are also on handouts. But the most important thing is to figure out what's the form of the solution, and all other everything else is just computations. So let's say that we have a second order differential equation of this form: x double prime plus x prime plus x is equal to t squared. You know that the solution to this is sum of a homogeneous part plus some particular solution. We know this from before. now we know how to figure out what's this solution of the homogeneous part. Now we only need one particular solution to this dE. And there are two ways. Either we guess or use variation of constants, but variation of constants really requires quite a lot of computations. So let's try to guess what would be the form of the solution. So xp of t, I ask you if you would dare to guess what would be the solution. What would be the form of the solution? So you have here second derivative, first derivative, and a function, so without derivative. So you see that on the left-hand side, we can expect to get three unknown coefficients. And on the right-hand side, we have a polynomial of degree 2. So on the right-hand side, the polynomial of degree 2 is determined by three coefficients, by the constant term, then the linear part, and the quadratic part. So if we try to guess what would be the solution, it should be something, some function, such that the sum of the second derivative, the first derivative, and the function will be a polynomial of degree 2, and the coefficients will be exactly 1, 0, 0. So what kind of a function should we take to get a polynomial of degree 2 on the left-hand side? Quadratic function, yeah. Quadratic polynomial. So at squared plus bt plus c. If we compute xp prime of t, we get 2at plus b. And if we compute the second derivative of t, we get 2a. And we plug those three expressions into our differential equation and get a system of three linear equations. So this gives us of three linear, so a system of three, a 3 by 3 system. This gives us a 3 times 3 system of linear equations. So whenever you have a polynomial on the right-hand side, you try for the particular solution, you just try to plug in the polynomial of the same degree, but with unknown coefficients. And what you will get will be a system, a linear system in those coefficients. Okay, and let's look at two other examples and just guess what would be particular solutions. And then we end for today. So the other example will be x double prime minus 3x prime plus 2x is equal to e to 3t. Again, x of t is homogeneous, the solution of the homogeneous part plus a particular solution. We know how to solve the homogeneous part. And now my question is, what would be the guess for the particular solution? So it should be some function such that when we differentiate it twice, on the left-hand side, we will get e to 3t to 3t. So when we differentiate this function and when we also differentiate it again, we still should get just exponent to exponential function with exponent 3t. So what would be your guess? Sorry? E to 3t times 1/3. Okay. Yeah. So maybe not exactly 1/3, but yeah, some coefficients times e to the power of 3t. Yeah. So the guess would be a times e to 3t, because if we take the derivative of this function, it's always it stays the exponential function, only the coefficient changes. So in particular, the derivative is 3a times e to 3t. And the second derivative is 9a times e to 3t. And then we plug this into our initial dE and compute a. So whenever you have an exponential function on the right side, you can try with the same exponential function, just that you allow coefficient to be non-zero, to be undetermined, and then you compute it from the differential equation. And the last example is x double prime minus x is equal to e to t. So what would be the particular solution in this part? What would be the guess for the particular solution in this case? A times, yeah, that's a good guess. A times e to t. It's almost correct, but the problem in this case is that this is also the solution of the homogeneous part. So if we solve the homogeneous part, x double prime minus x is equal to 0. The eigenvalues are 1 and -1, so the solutions are e to t and e to minus t. So this is in fact the solution of the homogeneous part. So in this case, we won't be able to get e to t on the right-hand side. In the previous example, we didn't have to check this, but 3 wasn't the solution of the homogeneous part, because the homogeneous part has has roots 1 and 2. E to t times b. In this case, the problem will be that this t times b will stay in the exponent on the left-hand side. So when we will compute the left-hand side, this b should eventually become 1, but it won't. So it will be the same exponential function. So we don't have a choice here for the exponent. The exponent must be e to t. But it turns out that in this case, we can add t, and this works. So you can try, so we can do it quickly. So exp derivative is a times e to t, t plus e to t. And then the second derivative is a times e to t times t plus 2at. We plug in the initial differential equation, and what we get is a times e to t plus 2 e to t minus a times t e to t. So the left-hand side. On the left-hand side, this part with t cancels out, so subtracts, and it remains 2a e to t. and it should be equal to this e to t on the right hand side. So a is equal to 1/2. So it always works if lambda, if the lambda on the right hand side is also the root of the characteristic polynomial, then we have to add t. If we had higher order differential equation, then we would have to add t to the multiplicity of the root. Okay, this is all for today. Are there maybe any questions? Maybe questions on chat? Okay.